In this lecture video, we are going to learn how to evaluate an integral using trigonometric substitution. At the top of this note sheet, I have some information that goes back to Math 172, trigonometry. I have the 3 Pythagorean identities, as well as the right triangle definitions for the 6 trig functions. You may have learned that when you learned SOHCAHTOA. As we go through these examples, you will see how all of this will play a role in what we're trying to do. Here I have a table, and in this table I have 2 columns, a column of radical expressions, all these different expressions with radicals that show up, and then in the second column I have the appropriate trigonometric substitution that we are to make if we see such an expression. And then I have some blanks here, and we'll fill these blanks out as we go through the examples. So what we're going to see in this lesson is we're going to see integrals as such, where we look at the integral and we say, well, maybe we could do this with a u substitution. I will quickly point out that if you tried u sub and you let u equal what was under the square root, you would quickly see that your derivative of negative 2x dx is not going to work for the u sub because there is no x dx in the integral. There's just an x. There's just a dx in the numerator. There's not an additional x with it. Furthermore, that substitution does not take care of this x squared. Perhaps we could do a double substitution, but what I want to show you how to do here is a trigonometric substitution. Another thing I want to point out before we get into the trig substitution, because I would hope that you would look at this integral and maybe that this 9 minus x squared under the square root would take you back to section 5.8, where we saw things like a squared minus u squared under the square root. And then we integrated that to get arc sine. However, the difference here is that our integral had that x squared in the front of the square root in the denominator, this x squared right there, so that I'm not able to apply that rule from section 5.8. So now that we've talked about what we're not able to do, we're not able to do u sub, and we're not able to do an inverse trig integral rule. Now let's get into the trig substitution. So I have highlighted that square root of 9 minus x squared under the square root, and I notice that it looks like this radical expression here. So because those two match, and I do want to clarify, it looks like the first one and not like the last one, because remember that a is a number in these cases. A is a number. So because we have the square root of 9 minus x squared instead of the square root of x squared minus 9, that is why we're using the first one and not the last one. So first, just to make this look like the integral that we're working with in the rule, I'm first just going to identify that we're saying our a squared is 9, our u squared is x squared, our a is 3 then, and therefore our u is x. So this here, this little gray cloud is just so you can see how what we have in our integral fits that. Please do not get confused. When I use u right here, I am not talking about this u that I'm actually going to be doing the substitution with. I'm just making it fit the form that we have up there. So what the substitution tells me to come in to do is to come in and to let u equal 3 sine theta. And I put 3 because our a was equal to 3. Well, if u is equal to 3 sine theta, I can see here that u was x when I match this to that form. So I have that x is equal to 3 sine theta. If x is equal to 3 sine theta, then that implies that sine theta is equal to what? If we were to take this equation, this substitution, and solve for sine, we would see that sine theta is equal to u divided by a. Similarly here, sine theta is equal to x divided by 3. And this is true in general. Now from sine being equal to x divided by 3, I can now go and set up a right triangle, put theta in that triangle, and I'm going to go and use SOHCAHTOA. Sine is opposite over hypotenuse, so I'll make the opposite side of that triangle x and the hypotenuse of that triangle 3. If I were to use Pythagorean's theorem to solve for the missing side of the triangle, I would find that the missing side of the triangle were equal to 9 minus x squared. That's from a simple Pythagorean theorem. It is not a coincidence that this 9 minus x squared is also matching that 9 minus x squared. It's the whole purpose of this table. This table tells you if you see this expression, use this substitution so that now when we actually start substituting into our integral, things will work out. So let's see. I'm now going to start rewriting the integral to see if we can pick up all of the pieces that we have. So the integral has a dx in the numerator. And then in the denominator, it has an x squared. And that's multiplied by the square root of 9 minus x squared. Now I'm actually going to start substituting in. In the numerator, we have dx. Well, back here, we said that x was equal to 3 sine theta. If I were to differentiate both sides, I would see that dx is then equal to 3 cosine theta d theta. So instead of writing dx in the integral, I now have the integral of 3 cosine theta d theta. So we have actually started the trigonometric substitution so far. I do think it's important to note out that you do not get this line after you do the substitution unless you go back and think, oh, well, u was x, which is why we put that x right there. Now let's go on and take care of the x squared in the denominator. We have this x squared in the denominator. Well, if x is equal to 3 sine theta, then x squared, I'm going to square both sides of that equation, is equal to 9 sine squared theta. So I'm going to substitute 9 sine squared theta in the denominator for that x squared. And then we have the square root of the 9 minus x squared. So that's 9 minus, I'm not going to put x squared, I'm going to put what x squared is. It is 9 minus sine squared theta. So we've completed the substitution. I want to make sure to emphasize here, please note that we started with an integral that had only x's in it, and now we have an integral that has only theta in it. So that's how I know that we have completed the substitution. Now we have to simplify this integral, and hopefully we can use what we learned in previous lessons to be able to integrate this now trigonometric expression. So to start simplifying this, we have the integral of 3 cosine theta d theta over 9 sine squared theta. Under that square root, I'm going to factor out a 9, which will leave me with 1 minus sine squared theta. 1 minus sine squared is a Pythagorean identity. That is equal to cosine squared. So I have replaced the 1 minus sine squared with cosine squared using this identity. If I had solved that identity, I would see that cosine squared is equal to 1 minus sine squared. So now we can start simplifying some things because that 9 cosine squared is under the square root. So I will take the square root of the 9, and I will also take the square root of the cosine squared. When we do that, we're left with simply 3 cosine theta, because the square root cancels out the square, and the square root of 9 is 3. Now this 3 cosine theta will cancel with that 3 cosine theta, which leaves us with the integral. I can pull the 1/9 that's in the denominator out. And we have a sine squared in the denominator, and sine squared in the denominator is the same thing as cosecant squared theta. And we still have the d theta on the end of that. So we've simplified this integral down to the integral of cosecant theta, which is something that we definitely do know how to integrate. It should be one of our rules from 8.1. The integral of the cosecant squared. Cosecant squared is a negative cotangent theta. So I come back here, and I know that I have 1/9 times negative cotangent theta plus c. So we've actually integrated now. Now I can't box this in and say this is my final answer because this still has theta in it. And I want to make sure that I revert back to the original variable of x. So now it's our job to get rid of this cotangent theta that's in the problem, and we do that using the triangle. So I have all the sides on the triangle, and if I scroll up, thinking of SOHCAHTOA, if tangent is opposite over adjacent, then cotangent is adjacent over opposite. So I'm going to go in here, and instead of writing negative 1/9 cotangent theta, let's talk about what cotangent is. Cotangent is adjacent over opposite. The adjacent side is the square root of 9 minus x squared, looking at this adjacent side on the triangle, and the opposite side is x. And we still have that plus c. So we do get our final answer of negative square root 9 minus x squared divided by 9x plus c. Now looking at example 2, again, I have an integral where I have this radical expression that is showing up. When I scroll up, I'm trying to choose which of these three expressions do we have. Well, one, our integral has a plus sign in that square root, and so we're working with this second one here, where we have the square root of a squared plus u squared. It doesn't matter if the a and the u are switched because addition is commutative, unlike multiplication. So we are going to use the substitution that u will be equal to a tan theta. We have to figure out what is u and what is a. And we do that by matching them to what we see in the integral. So if you really want to see the a squared minus u squared instead of the u squared minus a squared, there's nothing wrong with rewriting the integral as the square root of 1 plus 4x squared. Especially if that helps you see that then u squared is 4x squared. Remember, u should have x in it. U should have the variable, and a should always be a number. And a squared is 1. So our u is then 2x because we take the square root to get u. And our a is then 1. Again, taking the square root to get 1. Now, we've already said that because this had the u squared minus a squared under the radical, that we were going to use the substitution that u was equal to a tan theta. This is what trigonometric substitution comes as. So one thing I do want to be clear on, the takeaway from this lesson is that if you see this in the integral, this is the substitution that you make. Now, when you make that substitution, it does tell you then that tan theta is equal to u divided by a. This equality here will help you make the triangle. So when we make these equalities here and we actually solve for the trig function, we use this to assign sides on the right triangle. And we'll do that in example 2 as we set up and solve for what tangent was equal to. So we've said that u is equal to a tan theta. We know that u is 2x, and we know that a is 1, so I don't have to write that. So I have that 2x is equal to tangent theta. That's already solved for tangent. I don't have to divide by anything because a was 1. So you can see I can write that as a 1 in the denominator, and recall that from SOHCAHTOA, tangent is equal to opposite over adjacent. So I should be able to use that equation that's been solved for tangent to set up a right triangle where I can put theta as either of the two acute angles and make the opposite side of theta 2x and the adjacent side of theta 1. If I were to use Pythagorean's theorem to solve for the hypotenuse, I would find that the hypotenuse was the square root of 4x squared plus 1. C squared is equal to a squared plus b squared. So we have our triangle set up. Now let's go back to our integral and start seeing what we need to be able to sub in. So when I go to the integral, the first thing I see in the numerator of the integral is the dx. If I want dx, I need to take the derivative of x. Well, if I want x, I need to solve for x. This equation says 2x equals tan theta, which means that x is equal to 1/2 tangent theta. Now that I know what x is equal to, I can differentiate both sides to see that dx is equal to 1/2, and the derivative of tangent is secant squared theta, and I still have that d theta on the end. So we've solved for dx. We're going to substitute that in for the numerator. We have a 1/2 secant squared theta d theta. That's substituting for dx. Now we go to the denominator, where we have the square root of 1 plus 4x squared. That's the square root of 1 plus 4. I'm not going to put x squared. Remember, we're trying to do substitution now. So if we'd already solved for x and saw that x was 1/2 tan theta, which means that x squared, square the 1/2 to get 1/4, and square the tangent to get tangent squared. X squared is 1/4 tangent squared theta. Okay, so we've done the substitution. We now have the integral only in terms of theta. Ideally, at this point now, we should be able to simplify this integral and be left with something that we can integrate. I'm going to go ahead and pull the 1/2 out in front of the integral. I'm left with a secant squared theta in the numerator with a d theta. And then in the denominator, I have the square root of 1 plus, I'm going to distribute that 4. 4 times 1/4 is 1, and so I'm just left with tan squared theta. Now I need to use a Pythagorean identity because 1 plus tangent squared is equal to secant squared, which I can see from the second Pythagorean identity at the top of our notes. So I'm going to replace the 1 plus tangent squared with a secant squared. It's still under the square root. There's no d theta in the denominator. So we have 1/2 the integral of secant squared theta d theta. And when we take the square root, we're only left with 1 secant theta. So one of those secants will cancel and leave us with the integral of secant theta d theta. Going back to our integration rules from 8.1, the integral of secant is natural log absolute value of secant plus tangent. So we have 1/2 natural log absolute value of secant theta plus tan theta. There's no limits on our integral, so now I will add the plus c. I cannot yet box this answer and say we are done because we still have theta showing up in our integral. We need to go back now and use the triangle to not write secant theta anymore and to not write tangent theta anymore. We have to remember that from SOHCAHTOA, secant is hypotenuse over adjacent and tangent is opposite over adjacent. So I'm going to go back to my triangle. It's important that you pick one of these angles to be theta because it determines where you place everything when you use SOHCAHTOA. If secant is hypotenuse over adjacent, then for secant theta, I have the square root of 4x squared plus 1 over the adjacent side of 1, so I don't have to write that denominator. All of that's under the square root. And then for tan theta, which is opposite over adjacent, the opposite side is 2x and the adjacent side is 1, so I don't have to write that division. And now that we have everything back in terms of x, we have our final answer for our integral. I would like to point out that example 3 is an example that could be done using u sub. Unlike example 2, where there is no x in the numerator, example 3 does have an x in the numerator. So I would just like to mention that if you saw this integral and your first thought was u is x squared plus 1, so du is 2x dx, and so 1/2 du is x dx, and I see this x dx sitting right there in the integral, you could complete this integral with u sub. I am not going to go through finishing that, but hopefully we will get the exact same answer that we would get if we do this with trigonometric substitution. And it is seeing this radical expression in the denominator that would make us think of doing a trig substitution, seeing one of these 3 expressions here. In fact, we have the same expression as we did from the previous example. So we still have that a squared plus u squared under the square root. So I can see that my u squared is x squared. And I can see that my a squared is 1. So u is x and a is 1. Because we had that u squared plus a squared under the square root, we are using the substitution that u is equal to a tan theta. Now that we know what u and a are, we have that x is equal to 1 tan theta. So tangent theta is x over 1, which is opposite over adjacent. We will use that when we set up a triangle. I'll go ahead and set up that triangle. I'll choose to put theta there. I'll make the opposite side of theta x and the adjacent side of theta 1, which does make the hypotenuse the square root of x squared plus 1. Now, if we want to go ahead and start working on our integral, which is the integral of x, I'm going to put the dx in the top. And then in the denominator, we have the square root of x squared plus 1. We need to start substituting in. So in the numerator, for the x, I'm going to sub in the fact that x is equal to tan theta. So I'm going to replace that x with tan theta. Then I have to replace the dx with something. Well, if I want dx, I need to differentiate x. So if x is equal to tangent theta, then dx is equal to secant squared theta d theta, because the derivative of tangent is secant squared. And we have the d theta on the end of that. Now in the denominator, we have the square root of x squared plus 1. I'm not going to put x squared. X is tan theta, so I'm going to put the square root of tangent squared theta plus 1. And hopefully, if you noticed in the last two examples, the denominator we will be able to simplify using a Pythagorean identity, because tangent squared plus 1 is secant squared. It is not a coincidence that that is under the square root, so that the square will cancel, leaving us with the integral of tan theta, secant squared theta, d theta, all over secant theta. Now, to continue simplifying before we integrate anything, I can cancel one of those secants and be left with the integral of tan theta, secant theta, d theta, which is something that we do know how to easily integrate because we know that the derivative of secant is secant tangent. So just popping back to 8.1, we do know that if we are integrating the product of secant and tangent, we would only get secant. So this is equal to secant theta plus c. We're not going to leave our answer in terms of theta. We're going to go back to the triangle and we're going to replace secant theta with its definition from trigonometry. Secant is hypotenuse over adjacent. So our final answer, the hypotenuse of this triangle is the square root of x squared plus 1. The adjacent side of this triangle is 1, so I don't need that denominator. And I will remember to add in my constant of integration plus c to get our final answer. As we start example 4, you may think that there is no radical expression in this because we don't see a square root written explicitly. However, you have to look carefully at that fractional exponent. Remember that I can rewrite this as the integral of dx divided by x squared plus 1 to the 1/2, because there's my radical, there's my square root of that 1/2 exponent. But this was all really to the 3/2. So this is all then cubed, right? Because if you think about rules of exponents, we combine these by multiplying, and 1/2 times 3 is in fact 3/2. So I am allowed to break this up like that, just so you can see that we do have a radical expression in our integral. It's just written in a different way. So now that we see that, let's set up what our u and our a are. I see u squared plus a squared under the radical. So I can see that u is x squared, a squared is 1. Square rooting, I see that u is equal to x and the a is equal to 1. Because we had u squared plus a squared under the radical, we use the substitution that u is equal to a tan theta. We know that u is x and that a is 1. So x is equal to tan theta, which is x over 1. Note that that does automatically give us a right triangle. We're using SOHCAHTOA. I assign the opposite side of theta to be x and the adjacent side to be 1, which does give me a hypotenuse of the square root of x squared plus 1. Now let's actually start our substitution. We begin in the numerator. In order to substitute for dx, we need to take the derivative of x. If x is equal to tangent theta, then dx is equal to secant squared theta d theta. That's just from taking the derivative of tangent. So I've gone ahead and substituted in for dx. Now moving on to the denominator. Under that radical, we have x squared plus 1. I'm not going to write x squared. I'm going to take x. If x is equal to tan theta, then x squared is equal to tan squared theta. So I'm replacing x squared with tan squared theta, and we still have that plus 1. That's under the square root. And that whole square root is still raised to the third power. Now we've seen a few times in here that using the Pythagorean identity, we can turn what's under the square root, tan squared plus 1, into secant squared under the square root, still cubed. The fact that the secant squared is under the square root turns it into just a secant theta that is still cubed. And we still have d theta in the numerator. Looks like I dropped it a couple steps back. Please make sure you have that d theta on your paper. Two of these secants will cancel and leave us with just the integral of 1 over secant theta, d theta. And 1 over secant is cosine. So we are integrating just cosine theta d theta, and we know that the integral of cosine is sine theta plus c. We won't leave our answer in terms of theta because we started in terms of x, so we'll look back at the triangle, and we know that sine from SOHCAHTOA is opposite over hypotenuse. So the opposite to theta is x, and the hypotenuse is the square root of x squared plus 1. And then I'll add in my constant of integration plus c. And there we have our final answer. Here in our last example, we do see a radical expression. I also see that there's a dx missing on the end of this integral. But I do see this radical expression of x squared minus 3. That looks like a u squared minus a squared. So I will say that u squared is equal to x squared and that a squared is equal to 3. Which does mean that u is x and that a is the square root of 3. Now, for the actual trig substitution that we're going to be using, let's go up to the table and see what do we do when we have u squared minus a squared on the inside of the integral. We substitute in that u is equal to a secant theta, which of course would then mean that secant theta is equal to u over a. I just divided both sides of this by a. And then I can use secant being equal to u over a and the fact that secant is hypotenuse over adjacent to set up a right triangle. So we are going to be using the substitution as we saw in the table that u is equal to a secant theta. We now know that u is x and that a is the square root of 3. So we have x is equal to root 3 secant theta. From that, I'm going to go ahead and do two things. I'm going to solve for secant to see that secant theta is then equal to x over the square root of 3. Doing that, I should be able to then make a triangle. So I should be able to make a right triangle, make theta either one of the acute angles in the triangle. It doesn't matter if you put theta up there or if you put theta down in the corner where I have been putting it. What does matter is the fact that secant is equal to the hypotenuse side of the triangle over the adjacent side. So wherever you put theta, the hypotenuse is definitely over here, x, and the adjacent side is next to theta. This is opposite, so I'm not going to put it there, but the adjacent side of root 3 I will put right there. If I had solved for the opposite side with Pythagorean's theorem, I would have gotten x squared minus 3. So we have the triangle set up. The second thing I'm going to do, because I know I'm going to need it when I come to my integral, is I'm going to go ahead and take dx, because I can see here when I start my substitution, I'm going to have to sub in for dx. So if x is equal to root 3 secant theta, then differentiating that means that dx is equal to the square root of 3 secant theta tan theta d theta. So I just differentiated root 3 secant theta because the derivative of secant is secant tangent. So now let's come over here and start setting up our integral. I want us to pay very close attention to these limits. This is our first example that we're seeing with limits. We're going to discuss how to handle those. So for now, I'm not going to put any limits on the end of my integral. Those are x limits, and we're doing a substitution to get us out of x and into theta. So let's start with the numerator. In the numerator, we have the square root of x squared minus 3. I'm not going to write x squared because I know that x is root 3 secant theta. So I have root 3 secant theta squared instead of x squared minus 3. All that's under the square root. In the denominator, I just have x. Well, x is just root 3 secant theta. And then I have dx multiplied at the end, which is root 3 secant theta tan theta d theta. Now, before we start simplifying things and seeing what can cancel, let's talk about these limits. So the original problem started off in the variable of x, because I can see here I'm integrating with respect to x. We are switching the problem to, that's not a good color. We are switching the problem to now be integrating with respect to theta. So we started off with x limits. And now the limits that I'm going to use on this new integral need to be theta limits, because now I'm integrating with respect to theta. In order to get from x limits to theta limits, what we need some kind of equation that tells us theta is equal to something in terms of x. So I need to be able to solve for theta so I can change x limits to theta limits. Well, the only equation that I have that could help me solve for theta is this equation in here, where we say that secant theta is equal to x over root 3. If secant theta is equal to x over root 3, then theta is equal to secant inverse of x over root 3. I just solved for theta by taking secant inverse of both sides. So now that we know that theta is equal to secant inverse of x divided by root 3, maybe now we can change these limits to theta limits. So we started off with an upper limit of 2. Well, when x is equal to 2, let's see what theta is equal to. Well, we know it's secant inverse of x over root 3. When x is 2, we have secant inverse of 2 over root 3. And secant inverse of 2 over root 3 is the same thing. This is going back to 172. So if you need help with what I'm writing now, please do reach out to me and let me know. Secant inverse of 2 over root 3 is the same thing as cosine inverse of root 3 over 2. I've taken the reciprocal of what was on the inside. And cosine inverse of root 3 over 2 is pi over 6. The lower limit of the original integral was root 3. So plugging that in, I have secant inverse of root 3 over root 3, which is just secant inverse of 1. And secant inverse of 1 is equal to 0. So our limits on our new integral are from 0. I'm going to erase this so I have some space. But the limits on the new integral run from 0 to pi over 6. So I want to pause here and encourage you all. If you have any questions about how I'm getting those new x limits, please do take a second and shoot me an email. I'm more than happy to meet with you on Zoom to go over that change in limits. So now let's actually start simplifying this integral. We can cancel some things out. We can cancel out the root 3's. We can cancel out the secant thetas. Let's see what we have going on when we simplify what's under that square root. I'm going to square the root 3 to get 3. And I'm going to square the secant theta to get secant squared theta. And from that, we are subtracting 3. In the numerator, I have a tan theta d theta that's left. And everything in the denominator canceled, so I don't need to write the denominator. We can factor out a 3 under that square root to be left with secant squared theta minus 1. I can use a Pythagorean identity on the secant squared theta minus 1 because secant squared minus 1 is tangent squared. So under the square root, we have 3 multiplied by tan squared theta. And then outside of the square root, we still have the tan theta d theta. I can pull out the root 3 part of that integral, which leaves me with the tan squared under the square root, which of course will just turn into a tan theta. And that when we multiply that with the other tan theta that was already in the integral, we are integrating tangent squared. Now the integral of tangent squared goes back to when we learned about trigonometric integrals. If I were integrating tan squared, I'm looking back in 8.3. So when there are no secant factors and the power of tangent is even and positive, convert tangent squared into a secant squared factor and then expand and repeat if necessary. So I'm going to take the advice from 8.3 where we learned how to evaluate trigonometric integrals, and I'm going to convert the tangent squared into a secant squared factor using a Pythagorean identity, because tangent squared is equal to secant squared theta minus 1. I do know how to integrate each of those terms. I do know that the integral of secant squared is tangent, because the derivative of tangent is secant squared. And I know the integral of 1 is theta. And I will evaluate this from 0 to pi over 6. So we still have that coefficient of root 3 out in front. We apply our upper limit of pi over 6. And then we subtract and apply our lower limit of 0, not theta, but 0, to be left with root 3 times tangent of pi over 6 is root 3 over 3. From that, we are subtracting pi over 6. Tangent of 0 is 0, and 0 minus 0 does not change anything. So we are left with, I'm going to go ahead and distribute this root 3 in. Root 3 times root 3 is 3. And 3 over 3 is 1, minus root 3 multiplied by pi over 6. And that is our final answer.